Welcome, everyone, to this month's collective learning meeting. We actually already had the meeting beforehand, and we just want to re-record for better experience for our audience. So our presenter this month is Dr. Ivan Taylor. Ivan has worked as a defense scientist in the Center for Operational Research in Defense Research and Development Canada for over 33 years and is now retired, and is president and senior researcher at Policy Dynamics Incorporated, which he established in 2001. And
Great.
take
Thank
us
you.
away.
Thank you, Christine. I retired in 2012 from the Department of National Defense in Canada. And since 2012, I've been spending my full-time effort in system dynamics. I have a small business, as Christine said, in policy dynamics. I have a small business and consulting, and I spend most of my time actually mentoring in the System Dynamics Society. So I'm very busy with the one-on-one mentoring program and the peer mentoring program. So if anyone is interested in contacting me, you can get my information through Christine. And if you're interested in getting some mentoring. Anyways, if you do happen to get my mentoring, you'll see that I like to take the mystery out of system dynamics. And one of the ways I do that is by showing people how easy it is to take a model in system dynamics and convert it to an Excel spreadsheet. So that's what I'm going to do today, and I'm going to provide a few examples. So I'll just share my screen, and I'm going to start by showing you a model, a simple model in VenSim, and basically because you can see the stocks and the flows, and that'll help you understand how the stocks and the flows are implemented in Excel. So this is a simple model. I'm going to just do a simple population model. You've probably all seen this before. It's like a bathtub model, and which is commonly studied in introductory system dynamics. So I'm going to start with a population, and it's going to have a certain number of births, and that's going to be the inflow. And there'll be a certain number of deaths, and that'll be the outflow. And there will be an initial population, and there will be a birth rate, and there will be a life expectancy. I use Len Malinsky's naming conventions, and he's got, I think, a very good idea of naming stocks with the first letter capital and endogenous variables with small letters and exogenous variables with all caps. And that way you can see the parameters of the model in the exogenous variables, and the endogenous variables are the formulas inside the model. Okay, so I'm going to connect these together. So I connect the birth rate to the births, and the life expectancy to the deaths, and the initial population to the population, and the population to the births, and the population to the deaths. Okay, and now I'm going to introduce some formulas. So I'm going to start with a small population, just for this example. I'm going to start off with 1,000 people. And that'll be the initial population. And then I'm going to have a birth rate, and I will suggest the birth rate will be 0.04, which is it's going to be in people per year. So this is a 4 people per 100 people per year. And then I'm going to have a life expectancy. So let's make the life expectancy 72, and this will be years. And then we will put in the formulas, and the birth rate is going to be the population times the birth rate, and that's going to be in people per year. And the deaths is going to be the population divided by the life expectancy, and that's going to be in people per year. And the population will be the births minus the deaths, and with an initial population specified, and this will be in people. And I'll just go to the settings of the model, and I will have to save it first. So let's save the model. Okay, so I'll just go to settings now, and we can see that the units need to be the time step. The units of time have to be changed to years, and I'm going to change the step time to 0.125, and I'm going to look at the method of integration, and it's Euler integration. And that's what I use. It's a very simple methodology for doing numerical integration. Uh, and so that's how it's implemented in Vensim, and it's how it's implemented in most software packages for us system dynamics. And that's how I'm going to implement it in Excel. Okay, so I can check the units now in this model, and it should be okay. So the units are okay, and I can run the model, and I can look at the population, and I can see that we have an exponentially growing population. Okay, so now I'm going to just go to Excel now and show you how to build this model in Excel. So I have to label. So basically, I heard a very good explanation of system dynamics from Tim Warren, who you might know. And he said that if you want to explain what a system dynamics model is to someone who's not familiar, you can explain that every variable in a system dynamics model is a column in an Excel spreadsheet. And since most people are familiar with Excel, and since people would know what a column in an Excel spreadsheet is, I think that's a very good way of explaining how a system dynamics model works. And that's exactly what I'm going to do here. I'm going to develop the model now in Excel using columns in the spreadsheet. So the first thing I'll do is I'll introduce some labels. So I have the year, and I have the births, and I have the population. I'll just go back and I'll change this, and I'll put in the births. I'll put in the units of this is in people per year, and then I will put in the population, and that's in people. And then I'll put in the deaths, and that's in people per year. And then I have some parameters. And so I put the parameters in another column. And I'll put in the parameters and the values and the units. Okay, so the first thing I'm going to do is I'm going to have the start time. And then I'm going to have the time step. And then I'm going to have the initial population. And then I'm going to have the birth rate. And I will have the life expectancy. Okay, and now I will put in the start time of 0. I'll put in the time step of 0.125. I'll put in the initial population of 1,000. If you remember, that's what we used in the model. Let's take a look at the Benson, and let's say we go back to the birth rate. And we notice that the birth rate is 0.04. So I'll put that in the model, so 0.04. And the life expectancy, I go back to Benson, the life expectancy is 72 years. So I'll put in 72. And we can put units on this. So we have year, and we have year, and we have people, and we have people for people, per person, year, and we have year. Okay, so now I'm going to put in the equations. So we'll put in the equation for the start time, and we just we'll put in the cell F2. So we have the column F where all the parameter values are. So we'll put F2 equals F2 as the first start at the start of the program. So that's 0. And then we'll put the population at time 0, and that's going to be F4. And so we'll put in the population. And now we'll go to the births. And so if we go back to Vincent and we look at the births, we look at the births, we see that the births is equal to the population times the birth rate. So if we go back to Excel, we can say that this is births is equal to the population, that is C2, times the birth rate, which is 0.04, in cell F5. And what we have to do now is we have to anchor that value by putting a $ between the F and the 5. So when we cut and paste, copy and paste this the cell down the column, we won't be moving down the column in column F. We'll just be staying at the 0.04 value. Sorry, Christine?
I forgot to say this earlier when you presented the others. Technically, you're not copy and pasting. It's Excel that's changing the equations, and Excel understands what you're trying to do. Yeah.
Okay. I use the copy and paste feature of Excel. But yeah. Anyways, yeah. If you think it's better to explain it that way, that's okay. Oh, so anyways, I'll put in the deaths. So you go to the formula for Vensim for the deaths, and that's equal to the population minus the life expectancy. And if we go back to this, we go to this population and divide by F6. And we put this a dollar sign between the F and the 6 to anchor that value. And then we can work on the next line. So I'm going to start by working with the year. And so that's going to be equal to the year in step 0 plus the time step. And I'm going to put a dollar sign there because I have to anchor that. And then I'm going to calculate the population. And so if we go back to Vensim, we look at the population, that's equal to the births minus the deaths. And in Excel, the way you do that is you say that in the second time step, you start with the population in the previous time step, and then you add a value which is based on the time step times open bracket the births minus the deaths, and you have to again anchor the time step, and then you get a new value of the number of the population in the second time step. And then I take this value and I'll put it here. So now I get a new value for, let's change this here to show the values in general terms. Okay, so now I'll make the deaths, and so I will take the value here and I'll put it down here. So now I get new values of in the second time step. And if I go back to Vensim and I look at the births here and I look at the value shown in this table, you can see that there's 40 births in time step 0 and 40.1306 in the second time step. As you can see here, that's what you get with this in this value. And then if you look at the model again and you look at the deaths, you see that in time step 0 you have 13.888, and if you look at the model you have 13.888, and you have 13.934, and if you go back to that, so you have 13.9342. Okay, so just one of the things that also Kim Warren said, which I think is a great insight, is that when you're checking a model, you really only have to check that the model is correct in the first time step. And then, at least in Excel, it just has to be correct in the first time step. And then what I do is I copy this down here, and now I can say, well, now I think that the model will be correct for the rest of the time steps. So let's look at the value of the population in the Vensim model at time 4. So we'll go to the population and we'll look at the population at time 4. And we see it's 1,109 people. And if you look back at the Excel, you see it's 1,109 people. So I just wanted to show you that basically by implementing Euler integration in Excel, it's very easy to match a model in Excel to the model in Vensim or any other software package that implements System Dynamics if they're using Euler integration. Um, and when I talk to my mentees, I try to explain to them that that's really all there is to System Dynamics is you calculate stocks about new stock values every step based on the previous step and the inflows and outflows from that stock. And that gives you the value in the new time step. And basically you just do that, you just move through time in that way to get to a behavior over time graph for stock or flow or any kind of endogenous variable in the model. Okay, let me get into a more complicated example. I have I'm going to delete this, and I'm going to do a population of the world. And I have data for the population of the world from 1950 to 2020. And this population in the world is shown in this column here, the actual population. And here's a graph of the population. Which shows that I don't have a model developed, but I have the yellow dots represents the actual population in the world between 1950 and 2020. Okay, so I'm going to basically I'll go to I'll go to the parameters of the model. Let's just start with the first year of the model will be 1950, and that is this value here. So that goes in there, and I'll say the initial value of the population will come from here. So Y2 is the initial value of the population. And then, so now I have the initial population, and now I'm going to develop some parameters. So I'm going to have the birth rate, and I'll have the life expectancy. And I will specify that the initial value is 0.4, and the life expectancy is 72 years. And this, as I said before, is people per person per year, and this is years. Okay, so I'm going to do the exact same thing now. Oh, I have to put in the step time or the time steps, so I'll put that in here. And in this case, the time step will be 1 year. Okay, so now I'm going to calculate the births. So that's equal to the population times the birth rate, and I'll anchor that. And then I'll calculate the deaths, and that's equal to the population divided by the life expectancy, and anchor that. And then I will calculate the new time, which is the previous time plus the time step, and I'll anchor that. And I'll calculate the new population, which is the old population, plus the time step times the births minus deaths. And I'll anchor the time step. Okay, and then I will copy this down here. And then I'll run this down till 2020. And if I look at the graph now, it's not good. What I do wrong here? I think of that.
The depths.
Oh, that's should be anchored. Oh, that is that. Okay, let's try it again. That should be F2. Okay, sorry about that. Okay, so let's paste that. Okay, so now we have the model working, and we can see here that the model is much higher than the actual population. So, so at this point, to I want to get the model to match the actual population. So what I do here is I, I calculate the squared error between the model, and the model is in this column, which is just from C column. And then the actual population is shown in this column. And I take the difference between these two values, and then I square the difference. So you can see that these two values are different. And then I square the difference here. I put it in this column, and then I sum the squares of all the differences of all this. I take the sum of all the square difference and put it in this cell. So now I'm going to minimize the squared error between the sum of squared error between the model and the data. So I'm going to use something called solver, which comes with Excel. It's an add-in, but it's free, and it comes with Excel, and it's an optimizer. And what I'm going to do is I'm going to try to minimize. So I'll minimize this value, and by changing the the values here in this value, and this value here. So I'm going to change those values, and I'm going to try to minimize squared error. So if I run this now, I'm going to run the solver, and so it's trying to minimize the error. It takes a little while to run. Okay, so now it's found a new result, which looks a little better. It's definitely not perfect. I can try to run the solver again and see if it gets a better result. So I can try to run it again, and let's see, it's a better result. No, it looks like it didn't get a better result. So now, anyways, now you see that the model is a better fit. It's not perfect. So the reason it's not perfect is because we assumed that the birth rate and life expectancy are constant, and 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 that's incorrect because we know that the birth rate has been going down, and we know the life expectancy has been going up over the past 70 years. So I'm going to build a new model. I'm going to add a few more columns here. So, and I'm going to build a new model, and this model is going to uh, use a varying amount of over the 70 years. We're going to change the life expectancy and the birth rate. So here we have an initial birth rate, an initial life expectancy, a long-term birth rate, a long-term life expectancy, and a time to adjust the birth rate, and a time to adjust the death rate or the life expectancy. Okay, so that's now we're going to use this data. Well, we're going to put in a new thing where we're going to change the birth rate um, every every year. So this is going to be in people per person, and then we're going to change the birth rate, and this is going to be in people per person per year, and we're going to change this yearly, so it's going to be people per person per year per year. And then we have uh, and then we're going to put in the life expectancy, and this is going to be in years, and then we'll have change in the life expectancy, and this is in years, per year. Okay, so now we put in the initial birth rate in the first row, and we put in the initial life expectancy in the first row. And then we're going to use a simple goal gap model. So we're going to say that the change will be the long-term life expectancy, or the long-term birth rate, minus the current birth rate divided by the time to adjust rate. And so I'm going to anchor these values here. And then do the same thing for life expectancy. It's going to be a goal gap. So we'll take the long-term life expectancy minus the current life expectancy divided by the time to adjust the life expectancy. And we will put in the values here. We'll anchor them and we'll do that. And then the new birth rate is equal to the old birth rate plus the time step times the change. There's only one inflow, and it's a biflow. So it's both an inflow and an outflow. And here, and then we have this is now the previous value plus the time step times the change, and I will anchor that time step, and I get a new value. Pause. Okay, so now I'll get the new value of the change, and I'll get the new value of the change in life expectancy. And now I'm going to go back and I'm going to change this formula for births is going to be equal to, oh, sorry, this is the new formula for the births is going to be equal to population times the birth rate in the first time step. And the deaths is going to be the population divided by life expectancy in the first time step. And I'm going to copy those down here. And now I'm going to take this row and repeat it for 7 years. And now let's take a look at the graph. And we see we still basically have the same problem. So we're going to try to minimize the squared error now. So I'm going to use the solver, and I'm going to still minimize the squared error here. But now I'm going to change variables here for birth rate. Now I know that I looked up life expectancy, and I found that the life expectancy in 1950 was 46.5 years, and the life expectancy in 2020 was 72 years. So I'm not going to change these. I'm going to allow these to be the same values. I'm going to only change the birth rate. I'm going to find birth rates that give the best fit to the model based on these life expectancies. So basically, you can see here that the life expectancy has increased from 46.5 years to 72 years over 70 years. So now we have a new fit, and you can see that this is quite a bit better than the previous fit that we had. Uh, so uh, that that's one way to do the modeling of life expectancy and birth rate. I'm going to do one more example, and that is a little more complicated. It's going to be using a lookup table. So so I'm going to take this a lookup table here, uh, and I'm going to move it over here, and actually, I'm going to insert a lookup table here, um, that I okay. So now we have a new model, and what this is a lookup table. You may be familiar with lookup tables in Benson, and this is an Excel implementation of a lookup table. So we have values for the year that go from 1950 to 2020, and we have values for the birth rate for each of those years, and we have values for the life expectancy that I looked up on on the internet for the years from 1950 to 2020. So these are actual values that I found online. But the question is, we don't know necessarily what the birth rate is, so I'm going to calculate a lookup table for the birth rate. So this is, I have the formula here, and I'm going to just, I'm going to now go here, and this will now be uh, equal to C2 times birth rate, and this is equal to C2 times divided by life expectancy, the death rate. I guess that should be life expectancy. And okay, so now I'm going to copy this down. So, oh, I see. We don't have a value here. And then I'll oops. Okay, so now I have the life expectancy and the birth rate based on this lookup table. So you can see that it uses linear interpolation between the values of 1950 and 1960 to get the value in 1921. Okay, so now I'm going to, again, I'm going to try to minimize the squared error. So I'm going to go to the solver. You can see the model is not a good fit here. And you can go to the solver. And I'm going to again minimize the squared error in this place here. And this time I'm going to change the values in the table here. These values here I'm going to change these to try to get a better fit. So let's do it.
While we're waiting for that, Ivan, I forgot to ask, are you willing to share this Excel?
Sure. I can Excel. I can change. I can share the Excel. Sure. I probably should have. I'll, I'll I'll fix it up maybe a little bit before I share it to sort of
Mm,
show each step of the model rather than me overwriting the columns. I'll actually try to identify, which models are which in the columns. Is that okay?
yes. You also could have said you don't want to share. I understand you're also a consultant, so yeah.
No, I want to share the idea that Excel is useful, and if people can appreciate, but by learning by looking at these models, I think it would be great.
Mm,
Okay, so it's found a fit, and we can now look at the graph, and this is the best fit we found so far. Um, okay, um, that's all my presentation. Um, if you have questions, you can take them. So, um, Christina, are there any questions?
yes. Thank you for presenting, Ivan. And I have a couple questions. Can you provide an example of a more complex model?
Yeah. This is basically what makes a model more complex is there's just more columns. So this is a model that I developed for it's called my diversity model, and actually I'll be presenting a version of this model at the conference in Norway if the paper is accepted. And this is an idea that I had for trying to employ, hire, and promote indigenous people in a company that is involved in Canada. So this is something I'm doing for my consultant. So this is the model. And this is the interface that I use, and this is the model. So you can see here that we have a lot of columns. So each of those columns is an endogenous variable, and as you can see, it's a very large one. And so it's got about maybe uh, 36 endogenous variables. Um, I suppose I could share this model as well if you're interested. Um, but it is quite a lot to understand. But one of the things is that one of the reasons I like Excel is because when it's set up like this, I have the model here on this spreadsheet, and I have the interface on this spreadsheet. So I can hide the model. I can actually hide this spreadsheet so that people don't have to worry about what is in the model. But of course, I can show it to people as well if they're interested in the details. But what I like about Excel for doing these kind of models is these are the output graphs. And so if I have all of the parameters in the model listed in this table. So here are all the models in the all the parameters in the model, and they're all in one place, which I find very convenient compared to Vensim, because in Vensim you have to click on the variable name and look at the value in the that's stored in the equation to find out what the value is. And sometimes if you're making a lot of changes, you can get confused and have make changes that you didn't realize you made. But right here, we see that we have all of the parameters of the model in one place. So I can change a parameter. So let's say I change this parameter here from 1% to 2%. And what that does is that immediately changes the graphs. So if I change it to 5%, I see that the graphs change automatically. So it's I find that very convenient to be able to work with the model and basically change a parameter quickly and show the results of the change in graphical form as soon as you hit the enter button. And that's one of the reasons I like Excel for presentation purposes.
And,
Any other questions?
oh, this is related to what you were talking about. The benefit of using Excel versus the commercial software. I think you already answered that. And you uh, earlier you also mentioned about something about saving.
Oh yeah, yeah, yeah. One of the things, like if you wanted to build an interface like this in in say Stella Architect, you can build a beautiful interface in Stella Architect. Um, However, when you put the version online for people to run, um, there's no option that I know of to save a run permanently, because when you go back to the website, you have to start over again. Whereas in this software in Excel, if you want to keep a run, all you have to do is save the file and give it an appropriate name to be based on to indicate what parameters you used in that run. So it's somewhat similar to Vensim in that way that you can name the file um, based on the parameters. But in Vensim, I think you only save run, um, and and uh, and if you want to go back to previous parameters, you have to go back and change the values before you save the model again. So uh, so yeah. Anyways, I like the idea that you can save a spreadsheet quite easily. And of course, the other reason I think this is Excel is a nice tool is because people say clients that I'm familiar with or that I'm working with are familiar with Excel, and so they're not afraid of using Excel programs. They're familiar with them, and everyone has Excel on their desktop. They don't need to learn how to manipulate some special software to do a run of a model.
Mm.
Uh, so uh, and I know that you are losing a lot of detail because you don't necessarily have all the diagrams in one of the software tools like the stock and flow diagrams and the causal loop diagrams. But most of my clients, they're primarily interested in the results of a model. They're not necessarily interested in stock and flow diagrams and the causal loop diagrams. Um, I, you know, so I find this a nice way to show results to a client.
However, as you've shown, you also build a Vensim version to check your numbers.
That's right. That's right. I use the Vensim PLE Plus, and most of my mentees use Vensim PLE because they're learning system dynamics. And so what I generally do is I build the model in Vensim first because I want to get the structure correct. And then I take the formulas, basically the way I did today, and convert them to an Excel spreadsheet. And then, of course, I need to verify that I didn't make a mistake. So I make sure that the results of the spreadsheet match identically to the Vensim PLE plus run that I have. So once I'm convinced that the spreadsheet is exactly the same as the Vensim model that I built, I can then start working directly with the Excel model, and I don't have to necessarily go back to Vensim.
Thank you. I think that's all I have. Though I do have some other random questions, but it's not specifically about Excel. So I don't know if you want to answer these on record or I can cut them too.
I think we'll cut it at this point. I've used up my time, and just make I just want to say that if anyone wants more information, contact Christine, and she'll give you my email address, and you can contact me directly by email, um, and uh, I'd love to work with you as a mentor or as a colleague if you're interested in learning more about how to do system dynamics in Excel.
Thank you.
And another plug, a plug that I guess is a plug for myself is that I'm in the process of writing a book on system dynamics in Excel, and I hope to have the book finished by next summer. So maybe if you're interested in getting a book about doing models in Excel, you can look up that book.
Thank you.
Okay, thank you, Christine.